In this fourth application, summation of series, we are going to learn about summation of series that involve complex numbers. But to begin with, we have to recall something that we have learned previously in the lower year. In particular, in year 4, you have learned something called a GP. What is a GP? A GP is actually a series where you have one term leading to the next term by the multiplication of a common ratio. In this case, the common ratio is R. You have learned in year 4 that in the case of an infinite series, this infinite series will converge, or it has a finite sum, provided this condition holds true, which is the absolute value of the common ratio must be lesser than 1. And in year 4, you were given this formula, or maybe you have already learned the derivation of this formula. So in year 4, if you could recall, all these numbers that you dealt with in year 4, A and R, they are all real numbers. There was also another series that you learned before in the earlier years called the binomial series. If you have an expression that is like this, 1 plus x to the power of n, in the event that n is not a positive integer, you have learned in the earlier year that this can be expanded using what is known as the binomial series. And this series goes on infinitely. And in the earlier years, you also learned that these x's, in the earlier years when you learned this binomial series, all the x values that you learned, they were real numbers. What happens if we replace the x in this expansion or the r in this expansion with a complex number? What will happen? Let us study this issue by first and foremost looking at the finite series. In a case where you have a finite geometric progression, you have learned in the earlier year that this finite series adds up to this expression. It can be easily proven. You can refer to your earlier set of notes to recap how this expression was derived. Now, going by the same basis, if this R is now replaced with a complex number to give you a finite geometric series where the R is now Z, where Z are complex numbers, going by the same argument that you have used before for this, you will find that you will arrive at the same expression, in this case 1 minus z to the power of n over 1 minus z. Of course, the a is here. Right? So if you were to look at this finite series using the same method you have learned previously for the real number case, you find that even when these are complex numbers, the same formula is easily derived when the series is finite. Now, so for the finite case with this formula, we want to now study what happens if we have an infinite series where these z's are complex numbers. To establish the result for the infinite series, we have to first and foremost digress and study what happens if we raise a complex number, a generic complex number such as this. If we raise a generic complex number z to the power of n, what actually happens? Now, given the generic complex numbers, if you raise it to the power of n, from the earlier theorem that they've learned, raising a complex number such as this to the power of n, you will get this. This is a result of the Moore's theorem. Now let's study this very carefully. If your r is actually 1, raising 1 to the power of whatever, raising 1 to whatever power doesn't change the modulus. That means no matter what, as long as r is 1, the modulus of this complex number will stay as 1. right? But if your modulus R is more than 1, raising this to a big power will make R to the power n very big. And on the other hand, if R is less than 1, raising this to a big power will make this number very small. So in the event when R is more than 1, equals 1 or less than 1, this will be the behavior of R to the power of n. At the same time, what will happen to the argument? The argument will just go in multiples of theta, whatever the n is. Right? So this raising this to a certain power will actually in effect cause it to rotate, cause this rotate. So if you have the case where R is 1, raising it to high power will basically make the complex number z rotate around a unit circle. Let me show you this in diagram. So in diagram, right, if your R is 1, by raising it to big power, it basically means that complex number just revolve around the circle. Why the circle? This is a unit circle. The modulus is always 1. So raising it to big power will just make the complex number just go around the circle. It will not get out of the circle, just go around the circle. On the other hand, if your R is more than 1, apart from revolving around the origin, the value of R, because it increases, will make the complex number spiral outwards as you raise it to bigger and bigger power. On the other hand, if your R is less than 1, as the complex number revolves about the origin, you find that it actually spirals inward because the R gets shorter and shorter. So what you realize is, if you raise z to the power of n, you basically will get this result, that when R is more than 1, it spirals without limit, and when R is less than 1, it actually goes closer towards 0. And take a good look at these diagrams again. It summarizes what we have discussed earlier, which is when you raise a complex number z to a power of n, you have three possibilities: 1, 2, and 3. With this done, we are now ready to go back to what we intended to discuss. We actually wanted to look at this series when you have infinite number of terms. In another word, we are trying to look at this series when n goes towards infinity. So this is the usual way we would write an infinite series, expressing the infinite series in the form of a limit. Now, over here, right, as a finite sum, we have established a formula for the finite sum, and now applying limit to z to the power of n, we have this expression here. And based on what we have learned, when the modulus of z is less than 1, which is like this case, because it spirals inward, it eventually will go towards just 0. Or because the modulus gets shorter and shorter, it just spirals inward. Therefore, as n goes towards infinity, this complex number actually diminishes to just 0. As a result, you have a nice formula for the infinite series with complex number as the common ratio, and it turns out to be something that is very similar to what you have in the case of real numbers. And this formula is only applicable if the modulus of z is less than 1. And the reason is what we just explained: it actually spirals inward. With the result we have proven above, which is that this infinite series turns out to be this nice formula, if now we apply to find the real part of this equated to the real part of the left hand side, what will happen is the left hand side, using the Lemma theorem, right, this left hand side will turn out to be and will turn out to be an infinite series involving all the cosines. Can you see? Bear in mind that z squared, if z is r cos theta plus I sin theta, z squared will be r squared cos 2 theta I sin 2 theta. And because you are obtaining just the real part of z squared, you only have r squared cos 2 theta. And likewise for the zq. So you find that by applying to find the real part of this and the real part of this on both sides, we can reduce it to an infinite series of cosine function equals to a nice expression, which is this or this. And you have already learned enough in the earlier section of notes how you can actually so-called rationalize this to obtain the real part of this expression, which means it gives you a method to find the sum of an infinite series involving Trigo ratios. Likewise, if you were to apply instead of real, it will apply to find the imaginary part on either side, then you will have actually a series of the sine function equals to the imaginary part of this. And the same thing is that you're going to obtain a nice formula for an infinite series involving sine ratio. This is what I meant. So if you were to now apply to imaginary part, and you get a nice result. And we'll see more of this in the later examples. Now let us move into our first example in example 13. What we have here is actually an attempt to find the sum of a series that comprises a lot of cosines. If we were to try to find the sum of this series, chances are that you are likely to break this up. These are multiple angles. You are likely to break this up into single angles such as 2 cosine squared theta minus 1, and to break it out into a single angle as well for this, and so on and so forth. But it won't take you long to realize that actually trying to break up multiple angles like cos 10 theta or even cos 9 theta into single angle cosine theta is not an easy thing to do when the multiples of theta gets too large. So let's see how we can use our newfound knowledge to help us to find the sum of such a series in a very nice manner. To begin with, we want to actually introduce a z. Let z be the complex number ei theta. Now this complex number has actually a modulus. You don't see it here, it's actually a 1. So this complex number z is equals to 1 ei theta. The 1 is not written there. Such a complex number is, as you already learned, is called the unit complex number because the modulus is 1. For such a unit complex number, you want to realize that if you're asked to find the real of z, it's just cosine theta. To find the real of z squared is cosine 2 theta, and real of z cubed is cosine 3 theta. We will also need two results that we have learned previously. One is ei theta plus e minus I theta, and one is ei theta minus e to the power of minus I theta. These two results will come in handy in our manipulation below. So to begin with, let's start off with the left hand side. On the left hand side, our aim is to find the sum of this series. So one way out to finding this series, the sum of this series, is to rewrite this thing as the real part of this complex number. Remember, just like I told you that z is ei theta, and the real of z is exactly this. Z squared is cos 2 theta plus I sin 2 theta, and so the real part of z squared is actually cos 2 theta, and so on and so forth. So by writing this as the real part of this series, we can then apply the known result of a GP. This is definitely a GP. The first term is 1, the common ratio is z. So by applying the formula for the sum of a GP, I arrive at this. And then now, given that z is ei theta, z to the power 11 can now be replaced as ei 11 theta and ei theta for the denominator. So this expression is arrived from writing this as a GP sum and then replacing z with this. So our aim right now is to find the real part of this complex number. We have previously learned how to find the real part of a complex number by rationalizing this complex number. So one way to doing this is to multiply the numerator and the denominator by the so-called conjugate of the denominator. However, for this particular example, we will show you yet another way to try to so-called obtain the real part of this complex number through a different technique. So with this fraction, one way to go about doing this is to rewrite the numerator as this, and to rewrite the denominator as this. Now you check, if you take this times this, you get this. You take this times the second one, you actually get 1. Likewise for the denominator, if you take this times this, you add out the power, you get this. You take this times this, you add out power, you get e to the power 0, which is 1. Now, ask yourself, why do you think we want to rewrite this into this form? Why this into this form? And the answer is clear from what we have here. Remember, I told you we need the result that we learned earlier, that ei theta minus e to the power of minus I theta. There's a nice result that we can actually use. So using this nice result, I can rewrite these two into something simpler. You will have, in this case, for this portion here is expressed as this, and for this portion here it can be rewritten as 2i sine theta over 2. And this expression comes about when we take this to divide this. This 11 theta over 2, subtract theta over 2, you get actually 5 theta. So what I can do here is, having done so, I can now rewrite this expression. ei 5 theta is actually this. And upon cancelling the 2i and 2i, I'm left with this fraction here. And now you can abstract the real part of this entire fraction or entire expression as just this. Cool, isn't it? Look carefully, I've now obtained the real part of this expression by simply taking this, this, and this to give you the real part. So what we have effectively done here is we have actually found the sum of this series, which is actually a series of Trigo function. And how did we do it? We actually made use of the complex number ei theta, right? And you now reflect again. The trick here is to first and foremost rewrite this into a form where I can apply a GB formula, and later on it's just arithmetical to try to actually obtain the real part of the expression. And you realize that in trying to get the real part, you are seeing a new technique. It is not exactly the same as what you would do normally. Usually, as I said, we will multiply by the conjugate of this denominator. But here we are doing it slightly differently, and very quickly we got the result, the real part of this complex number, which is this, and this is actually the sum of this entire expression. Now think about it again. If you were to do this sum all on your own without the help of this idea, it can take really a while. Let us now look at example 14. In question 14, we want to actually find the sum of two series. The difference between example 14 and example 13 is that in the case of example 13, you have a finite number of terms. You stop at something like cos 10 theta in the earlier example. Whereas in example 14, in part 1 and part 2, you actually have infinite series. You have two infinite series. And like the earlier example, we are going to make use of complex numbers to help us to find the sum of series of Trigo functions. For this question, let's take the approach by starting off with letting C to be this and letting S to be this. Look carefully, C is exactly the part 2, whereas S is only a part. What do you mean a part of the part 1? Look carefully between part 1 and S. It is short of 1, right? Short of 1. Now, so letting C and S to be this and this respectively, what we can do here is we are going to add them up together. If you add up C and S, you have the 1, and then this one when added together, C plus IS gives you half open bracket cos theta plus I sin theta, which is written as EI theta. Likewise, 1/4 of cos 2 theta plus I sin, right? I of this one will give you 1/4 EI2 theta. And likewise, when I add up these two together, of course, C plus IS, 1/8 this plus I of this whole chunk will give me this expression. So by writing them in this manner, you find that now I actually have a nice GP. Can you see this can be rewritten and re-expressed into a form that you will quickly recognize that this is a GP, where the first term is 1. This is a common ratio. Can you see the common ratio? And what do you notice about the common ratio? This common ratio is a complex number, and you notice that the modulus of this complex number is half. The common ratio, which is a complex number, has a modulus of half, and that satisfies the condition that we need. The condition that we need is the modulus of the common ratio must be lesser than 1. In this case, it's half. It is less than 1, so I can actually apply the formula for infinite series of complex numbers, like what we proved earlier. And applying the formula, we now have 1 over 1 minus half EI theta is A over 1 minus R. Right? So what we intend to do from here is, we now intend to break this up into the real part and the imaginary part. We intend to abstract out the real part and the imaginary part of this complex number. So to do so, the typical step is to actually try to multiply the denominator by what? We shall see a short while later. Okay, one more step, tidying up first. So from here, we tidy up this one to become like this. It's just a simple arithmetic. By adding up these two together, I have a denominator of 2, which I bring it up here. So now our aim right now is to try to actually rationalize this expression. If you could recall, to rationalize an expression like this, right, which means you try to make the denominator just a real number. If you could recall, the step to doing so is to try to multiply both the denominator and the numerator by the conjugate. Okay, let's say once more. To rationalize this expression, we want to multiply the denominator and the numerator by the conjugate of the denominator. What is the conjugate of the denominator? Okay, the conjugate of this denominator is everything the same, except that instead of I theta, you have minus I theta. There's something you want to get used to, that the conjugate of this complex number is everything the same, except that the I theta is now changed to minus I theta, and the rest of the steps are just arithmetical. So for the numerator, you just have to multiply them like what you would do normally. 2 and 2 give you 4, and then 2 times this give you this. For the denominator, if you were to expand the denominator, you'll get 2 and 2 gives you 4. This complex number times this complex number, right? Minus EI theta minus EI minus I theta. When multiply this together, you will give you a 1. And then you take 2 times this minus this times 2. You tidy them up, you get this expression. So there's actually something that is missing here. Do you spot a mistake? I'm mentioning right now. There should be a 2 here. There should be a 2 here. Okay, let me add it in. Alright. There should be a 2 here. And then this ought to be 4. Alright. Okay, and then this ought to be 4. Let me just change it quickly. Okay, I think we are quite done. Let me go back to, okay, right. So over here, if you were to expand the denominator, this gives you 4, this and this gives you a 1, this times 2 and this 2 times this fellow will give me a 2 open bracket this fellow. And remember this result, EI theta plus E minus I theta is actually 2 cos theta. 2 cos theta with a 2 will give you a 4 cos theta. And for the numerator, right? For the numerator, this one is actually e to the power of minus I theta, which can be expressed as cos minus I sine. And then tidying them out, you now have the real and then the imaginary, right? The real and then the imaginary. So moving back to where we first started, we started off with c plus is. So obviously, if this is c plus is, c therefore must be the, okay, let me do a bit of tidying up. Let me copy this, and maybe I should put it right below so you can see it better. Okay, let me paste it in. Yep, I can see it better right now. Okay, so if you were to recall, we had c plus is, so therefore c must be this, and s therefore must be the imaginary part. So by so doing, we now can quickly produce the result for the first series. Be very careful here, no? Remember just now I told you that s, right? S doesn't contain the 1. So in order to find this series, you have added 1 artificially. You can see this 1 is the account for this 1. Because s itself doesn't carry 1. So it's 1 plus 8. Let me make the correction. There's going to be 4. And likewise, there's an error here. This ought to be 4 as well. And here we are. Okay, by comparing, our C is this, and our S, which is this, right? So the first series, you add the additional 1, and for the other one, immediately is the C. And we are done. So once again, you have shown how we can use complex number to actually find the sum of series comprising of sine function and series that comprises cosine function. Now let us look into a more complicated example in example 15. In this question, we are required to prove that the sum of this is equals to this complicated looking expression. For the sum on the left hand side, if you were to iterate the terms, you'll find that actually the sum on the left hand side is actually 1 plus x cos theta plus x squared cos 2 theta x cubed cos 3 theta all the way through to this last term. So to find the sum, the way to start off is we want to let z to be equals to I theta. If you let z to be equals to e to the power of I theta, then this expression on the left hand side can be written as this, the real part of this complex number. Taking x times z and raising the power of r for each term, you find that the real part of this fellow is exactly this. So what you realize is, from the original expression, which is hard to sum, we have actually re-expressed it into something that we are familiar with. This summation, if you look at it more carefully, is simply a GP, where the first term is xz to the power of 0, the second term is xz to the power of 1, and so on and so forth. So this is exactly a GP, where the first term is actually 1, and then the common ratio is xz. Using the formula for the sum of n terms of a GP, we will arrive at this. This is the common ratio raised by n minus 1, then the common ratio minus 1. So our job right now is to try to extract the real part of this expression, and to do so, we reintroduce back the z as your ei theta, and raise the power of n, you get ei n theta. Z here is ei theta. So in order to extract the real part of this expression, we have to multiply by the conjugate of the denominator both to the bottom as well as the top. Can you see the conjugate of this expression, bearing in mind that x is real, the conjugate of this expression is actually the same, except that I theta is now replaced as minus I theta. If you do your arithmetic carefully and accurately, this product will result in this. How does it come about? When you take this to times with this, right? You actually get n plus 1 for x and then you add up the power for these two, you get this. And then you take this times this and take this times this, you get these two terms. And the last term plus 1 is from minus 1 times minus 1. You get plus 1. As for the denominator, the arithmetic is something that we have also seen in the earlier questions. So to multiply the denominator, we take this times this times this, and so on, and then we tidy them up, we will arrive at this expression. You want to realize that over here, this expression of 2 cos theta actually came about when you add ei theta with e minus I theta. This is how the 2 cos theta comes about. So in tidying up this expression using the conjugate of the denominator, we arrive at this. And now to obtain the real part of this complex number, we just need to obtain the cosine function from here, the cosine function from here, and the cosine function from here, and thus we arrive at this nice looking or complicated looking expression that you're required to prove. So this is actually the first part of the question, wherein you're asked to find the sum of this series and to show that it is equals to this complicated looking expression. For the part B of the question, reads like this. For part B of the question, it is related to the part A, but in the case of part B, now you're dealing with 3 n terms. To find the sum of this series up to 3 n terms, you must try to relate this series with what you have proven earlier. To start off with, you realize that this one is now re-expressed as r equals 0 to 3n minus 1. Why 3n minus 1? Because earlier on in the original series, we are summing up from 0 to n minus 1, and this one has n terms. In part B, you want to have the sum of 3n terms, right? So that suggests to you that you should put the n as 3n so that you will have a total of 3n terms. But what is more difficult to determine is that in the series above, you must be able to actually, okay, maybe I should actually copy this thing down to show you. Okay, this series from the top. Okay, I'm going to copy below. Okay. This was the original series that we proven earlier, right? So as I said just now, we have changed the upper limit to 3n minus 1 because you want to sum up to 3n terms. But what is difficult in this question is you must be able to spot on a value of theta so that this entire expression matches this. Say again, you want to be able to spot on the value of theta so that the series will match this. And the value that you will spot on for theta, it has to be 2 pi over 3. Which means what I'm doing here is from the original series, I'm able to make use of this original series by first replacing n as 3n, and I spotted on a value of theta so that I will get a 1 minus minus plus minus minus and so on. Okay, so I spotted on the value of theta as 2 pi over 3. I plug it in here to give me this. You can try for yourself that if you were to write down these terms, it will match exactly like what you see here. Just to note, say when r is 0, right? When r is 0, this is x power 0. This will become cos 0, so that gives you a 1. And when r is 1, this is x, and this gives you cos of 2 pi over 3. Now we all know that 2 pi over 3 is a special angle, so cos of 2 pi over 3, we all know that it's actually minus half. Then when r is 2, you will have x squared, and you're going to have 2 times 2, which is 4 pi over 3. Cos of 4 pi over 3 is also a special angle, it's again minus half. And then when r is 3, you get x cubed. 3 times 2 pi over 3 is cos of 2 pi. Cosine of 2 pi is just a 1. That's why I got positive, in this case x cubed. So to be able to do the part B, what I'm trying to tell you is you must be able to spot on these replacement values. If you cannot spot on these replacement values, then you find that part B is very, very hard. Next, having spotted on the values for theta and also replacing n with 3n and now confirming that this intended series up to 3n terms is exactly like this, we are now ready to tidy up the expression from what we have proven earlier, from this expression they proven earlier. What we do here is replace the n with 3n, replace the n here with 3n, 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 and replacing all the theta with 2 pi over 3, we arrive at this expression here. Now, this expression is basically the same as what you have proven in part A, with the n replaced as 3n and the theta replaced as 2 pi over 3. And from henceforth, it is all arithmetical. Okay, so to go on from here, we take this times this, we arrive at 2 pi minus 2 pi over 3. We take this times this, we get 2n pi, and then this remains and this remains. Now, we all know from Trigo that cos of 2 pi minus an angle is just the angle itself. Because this is a complete cycle, so cos of a complete cycle minus 2 pi over 3 is just cos of minus 2 pi over 3. This is just the same, this is just the same. And then we also know from basic Trigo that cos of this is minus half. Cos of multiple of 2 pi. Multiple of 2 pi comprises 0, plus minus 2 pi, plus minus 4 pi, plus and so forth. Right? But anyway, in this case, we are talking about positive n. So it's going to be 0, 2 pi, 4 pi, and so forth. Cosine of multiple of 2 pi is actually 1. This is minus half. So I replace all these values that I know of. I got to this expression. And then I tidy up further. From this line to this line is just arithmetical, just tidying up. Like this and this gives you a plus, minus pull out, minus pulls up, you pull out a minus, right? You pull out a minus, and then now you tidy up this denominator, you get this nice expression, and one more line of tidying up leads you to this expression. Okay, so what we have done here in part B is we have made use of part A answer for this expression to work out a sum for this up to 3 n terms, right? And the strategy in this question is you must be able to spot on that you have to replace n with 3n and theta with 2 pi over 3, right? And that is actually part B. And in part C, right, you're asked to show that the limit of the sum as n goes to infinity. So when n goes to infinity, because of this condition, bear in mind x is real. When n goes to infinity, right, this expression will go towards 0 because a fractional number when raised to infinite power will be 0, and likewise a fractional number raised to infinite power will also be 0. So these two terms will dissolve, will just go off, and left with these two, and finally you get this line. And this is how you actually prove part C. In our last example, which is example 16, we want to learn some of the interesting techniques that we have in manipulating complex number expression. In this example, what we have here is we want to prove that this thing on the left can be tidied up to become this expression. And we intend to show that this can be done in two different methods. One of them is purely Trigo, and the other one is to use some techniques we saw previously. So let's start with the method 1. In this expression here, Trigo identities allows me to replace the cos theta as 2 cosine squared theta over 2 minus 1. This is so-called the half angle formula. Likewise, sine theta, according to Trigo identity, can be expressed as 2 sine theta over 2 and cos theta over 2. So for this method 1, we are purely using known Trigo identities. Whereas over here, we are going to capitalize on the fact that this expression, according to the Euler's formula, is expressible as e to the I theta. And to tidy up this expression, we are going to make use of a technique that we learned in the earlier example. This expression can be rewritten as like this. The reason why we are writing in this manner will become obvious if you are familiar with how you can tidy up an expression such as this. You'll see it in a while later. Now going back to method 1, from here we can then open out all the brackets, tidy them out to become this. And obviously from here you can see that they have a common factor of 2 cosine theta over 2. On the other hand, over here I can split this up into first number power n and then second number power n. Okay, let's see. After this line or after this line, what am I going to write next? Give yourself that 30 seconds to ponder over before I review it to you. Okay, not to keep it in suspense for too long. For the left hand side, you will simply raise this to the power of n, and for this other one, because raising this complex number to the power of n according to the Moire theorem, this becomes n theta over 2 inside and n theta over 2 inside here as well. So using Trigo, purely Trigo identities, I have managed to prove that this is equals to this. On the other hand, remember this one can be tidied up as 2 cosine theta over 2, a result that we have seen it previously. So on this side, I can rewrite this thing as e to the I n theta over 2, which will be rewritten as this. This can be written as this, and now for this one, which becomes this, and now you have 2 cos theta over 2 to the power of n. So I have shown you here 2 different methods, one purely Trigo and one using some of the techniques we learned previously to tidy up and show that this expression is equals to this. Let's go on to the part B of this question. In part B of this question, you are given a series that involve, what do you remember this? This means NC1, this means NC2, and so on and so forth. So how can we actually show that this is equals to this? If you observe carefully, before you go on, if you observe this carefully, you will realize that this one is simply the, okay, look at this one carefully. What's the relationship between what you see in this blue color and compared to this? That's right, you will realize that this fellow is actually the imaginary part of this entire expression. You can see the imaginary part of this entire expression. So you realize that actually to prove this result, it therefore has to do with what you see in the earlier calculation. So how do we actually manage this? One way out is to start off by letting an S to be equals to this, and then letting C to be this. So guess what am I going to do next? That's right, I'm going to rewrite this thing as cos plus I sine, or C plus IS. C plus IS will yield this expression. You want to note that when I combine these two together, cos theta plus I sine theta is EI theta. Cos 2 theta plus I sine 2 theta is EI theta power 2, or it's actually EI2 theta. Right? It's actually EI2 theta. So I can add them out term-wise, and I get this expression. If you notice this one carefully, you must be able to see that this expression is actually the binomial expansion of this. If you try to do the binomial expansion of this, right, you will see that it's exactly this. This is actually from NC0. NC0 EI theta to the power of 0, then NC1 EI theta, then NC2 EI theta squared, and so on and so forth. So this expression is exactly the binomial expansion of this. And in the earlier proof, right, this one can be rewritten as this, which is the same as what we had just now. So this expression is exactly what we had just now, and we're going to make use of it a while later. So now you intend to actually find this one, the S. In the left hand side, C plus IS, this expression, or which is this, right, is actually the imaginary part of the left hand side. Right, the imaginary part of the left hand side, which is therefore these terms, must therefore be equal to the imaginary part of this. And the imaginary part of this, like what I told just now, right? We have this result earlier on, right? The imaginary part of this expression, which is the same as this, is this expression times sine of n theta over 2. That's how you get the proof that that S is equals to this. Okay, so you can see the link between part B and part A, then you know that you have to work towards it. So one of the presentation that you want to actually do is to start off with this. It's very neat and nice. And lastly, for part C, you are asked to deduce this result. To deduce the result of this, right? You therefore want to try to link this to what you have proven earlier. And like in the example 15, for such type of question, you must be able to spot on an angle theta so that this expression on the left will actually match this. So let's look carefully. Obviously, by comparing this and this one, you will probably guess that n has to be 2015, right? So you want 2015 sine of angle, 2015 C2 sine 2 theta, and so forth. And if you look at them and compare them more carefully, you realize that actually the even terms, the sine 2 theta and the sine 4 theta, these terms must disappear. Why is it so? Because in this expression that we want to evaluate, there's only 2015C1, 2015C3, 2015C5, and so on. That means they only have the odd number terms, which means in order to spot on a value of theta, I must choose a theta so that all the even terms will die off. For the case of sine, sine function will die off if this angle, or the 4 theta, or the 6 theta, and so forth, they must end up with 0 or 2 pi or 4 pi and so forth. So which means I need to try to get this as a multiple of pi, 2 pi, 3 pi, 4 pi. Sine of such angles will always be 0. So judging from these two, what therefore would you think would you pick as a value for theta so that this will become this? Okay, at the same time, you want to realize that over here, right? If I put n as 2015 and then 1, right? This number must yield a number of 1 so that it will match, you see. So by some guess and check, after a little while, you will probably guess that theta ought to be theta over 2. Because sine theta over 2 is actually 1. So that's why this thing is a positive 1 times this. And then if you put theta as pi over 2, sine of 3 pi over 2 is a minus 1. That's why for nc3 or 2015c3, you have a minus. So I find that if I choose theta as pi over 2, it works well for the nc1 and nc3. And at the same time, it also works well for the nc2 because if theta is pi over 2, this becomes sine of pi, which is therefore 0, it will disappear. So therefore, from this guess and check, I therefore can deduce that I should choose theta as pi over 2. So putting theta as pi over 2 on the left-hand side, I therefore know that I will get this expression when n is 2015. So I will therefore put this as 2015 and put my theta as pi over 2 and pi over 2 and 2015. So upon reducing it, can you see over here, right? So you're going to have 2 cosine theta is pi over 2, so half theta becomes pi over 4. Cos of pi over 4 is actually 1 over square root 2 times 2 will give you a root 2. So you got root 2 to the power of 2015. At the same time, you're going to have 2015 times pi over 2 times half. Sine of this angle, if you do a bit of a guess and check or a bit of experimentation, you find that actually sine of this angle will end up with just minus pi over 4. Just take away 2 pi out of the way, you find that in the end you end up with just sine of minus pi over 4. And sine minus pi over 4 we all know is minus 1 over square root 2. So together with root 2 to the power of 2015, we should in the end obtain the answer of minus 2 to the power of 1007. And that's the answer therefore for the expression 2015C1 minus 2015C3 and so on and so forth. And that brings us to the end of the fourth application of chapter 4, and is also the end of the chapter 4. Okay, before I move off, I should probably let you see this calculation more vividly by showing you all the calculation in one snapshot. I'll just leave this for a little while longer for you to jot down whatever you want. Okay, so with this, we come to the conclusion of chapter 4 as well as the module notes. Thank you.